trying to do is say I love you.
Hey guys, today we're answering the question, why do we exist? Just to suffer. No, okay, too existential. How about, where did our world come from? Well, the short answer is from dust. To be more specific, from a dense molecular cloud. Galaxies are like cosmic vacuum cleaners, collecting all of the dust and gas floating around the universe. Even our own Milky Way gets its milky appearance from these collections of interstellar material. Once the gas and dust particles are very cold, and they get cozy and close enough together, they begin to collapse. Eventually, the potential energy of the system converts into kinetic energy and heats up, so much so that the center ignites and a star is born. That's not all. In addition to conserving thermal energy, molecular cloud spins, albeit slowly, and that angular momentum is also conserved. What that means is the star starts spinning, and it's faster than the cloud because it takes up less space. But not all of that momentum goes into the star. Some goes into the formation of planets, some goes into making binary or trinary star systems, and some of it goes into the stellar winds that blow away material. Sort of the universe's way of redecorating, I suppose. Gravity is drawn toward the center, which forces the leftover dust and gas particles to crash into each other like bumper cars, until they make a nice flat disk around the star's equator. This disk is what planets form from, and it's called a protoplanetary disk. Now the clock is ticking. The young star does not yet have the power to blow off all the excess material in the system, but we do need a lot of dust and gas to make all these planets. So how do we turn dust, rocks, and pebbles into planets? Well, gas particles tend to want to stick together. They feel the force of gravity from the star, as well as the centrifugal force and gas pressure. Small dust particles are coupled to the gas particles like smoke in the air. Over time, the dust collides and forms bigger objects. You get to the size of rocks around 1 centimeter in diameter, but they stop sticking together as easily. Imagine if you throw 2 rocks together. They don't just morph into one big rock. Instead, they bounce off each other or even shatter into smaller pieces. This makes getting to the planetesimal stage, around 1 kilometer in diameter, a little bit more difficult. These larger particles also move faster than gas particles. They feel a drag that makes them lose orbital energy. Now the object is not moving fast enough and the orbit has been disrupted enough that it begins to fall into the star. This is known as radial drift. At the distance from the Earth to the Sun, pebbles and rocks only have about 100 years before they fall into the Sun. So how do we form an Earth-sized planet with only 100 years? Obviously objects bigger than pebbles exist in the system. But how do we get there? One theory is particles grow the same way, by crashing into each other and getting bigger. One issue with this is it takes time, and with only 100 years, it's not much time to pull it off. Some scientists think that the dust settles into a flat disk around a star. It gets pulled in enough by the star to get very dense. The area then gets gravitationally unstable, collapses, and forms a planetesimal. However, the density required to make the area unstable enough to collapse is very difficult to achieve, as the gas mixes with the dust and reduces the density. The leading hypothesis for solving this problem is materials jumped from the centimeter size to the kilometer size. Gas and dust are strongly coupled to one another. Dust particles move to areas with more pressure, aka closer to the star. As the gas moves past other gas in the disk, filaments form that can trap the dust that's coupled to that gas, and these trapped pockets of dust can get dense enough to cause collapse, just like how a star forms. With a larger gravitational field, the new planetesimal can pull in more material and get bigger exponentially. Gravity also causes bigger objects to become more spherical, since the surface will have a uniform pull from gravity across the entire object. Planetesimals do not fall into the star as quickly because they have less surface area compared to their mass, due to their spherical shape. So why is this our leading theory? The dust can be trapped for longer periods, allowing more time to create planetesimals and even larger planets. We can also run computer simulations to map out how our solar system looks. The best fitting models for our solar system objects are where the minimum diameter for a planetesimal is 100 kilometers, and any smaller asteroids are just collisional debris. The Atacama Large Millimeter Submillimeter Array has been looking for exoplanetary disks that may shed further light into how planetesimals form. Scientists working on ALMA have found a disk with a young planet orbiting at about 100 AU surrounded by spiral arms, full of material that seemed to be feeding the protoplanet. This leads credence to the idea of dust trapping because these spiral arms may be the remnants of gas filaments that once trapped the system's dust and created the baby planet. Once those planetesimals finally show up to the cosmic party, gravity steps in. It helps pull in material and make these huge worlds we see today. See you guys next time.
I am trying to do is say I love you. Ooh, ooh, ooh.